Hello and welcome. So today is the last day of this course. So what we will do in today's class is to summarize all those things that we have learned so far. So hopefully in this course you have learned about the introduction of qualitative description of molecular symmetry, and also you have learned the way in which it can be used in both not only qualitative but in a quantitative way within the context of the mathematical framework group theory to predict various important molecular properties. So let's go through one by one what are the things that we have learned over the past 8 weeks. So we started with giving you an idea about the symmetry, and we said that this is something about the regularity or very much similarity or periodicity in certain way. So when we started talking about molecule, we started talking about the symmetry elements present there, and we also talked about how do we use those symmetry elements to generate the symmetry operations. So we identified that there are different symmetry elements. For example, identity, which is present in almost every object in this every object of this universe, and there are axes of symmetries, namely proper axis of symmetry and improper axis of symmetry. Within the proper axis of symmetry, we learnt about the principal axis of rotation. So that is the highest order of proper axis of rotation. And we learnt about inversion symmetry, that is the element was center of inversion, and we also learnt about the mirror planes. So we learnt about the symbols that are provided for each of this element as well as the operation. So we had E for identity, Cn for proper axis of rotation of order n, Sn for improper axis of rotation of order n. We had I for inversion symmetry, and sigma for the reflection planes. And the symbols for symmetry elements were also used for the symmetry operation purposes. So only thing is that the number of one particular operation is being operated was denoted by that number in as a superscript. So for example, Cn operated 3 times was written as Cn3, as if Cn to the power 3. So after learning about the symmetry elements and symmetry operations, when we started identifying those elements and also started understanding how to operate the symmetry operations on any given object, primarily the molecular structures, then we looked at the possibility of expressing this symmetry operations using some mathematical framework. So we introduced the a concept of group theory first. So we started with abstract mathematical group theory. So while we defined what a group is and what are the conditions for a given set of any distinct object to form a group was discussed. So we had 4 set of rules. So existence of identity, and this closure property and associativity. This had to be ensured before we can call a set of any distinct objects as a group when we define a particular binary operation in it. And also we needed a unique inverse for each and every element of the within the set. We needed a unique inverse for each and every element of the set. And apart from that, we also learned that additionally, if you have commutation relation valid for each and every element of that particular group, then it's an abelian group. And after learning this basic mathematical concept of group, we figured out that our symmetry operations also can form a group, because all the conditions for calling a set a group was satisfied by the symmetry operations of any particular molecule. And this symmetry point groups or the simply point groups were formed for any given particular molecular structure, and we learned a systematic way to assign the point groups to any particular molecule. So we learned these steps where we started with any given molecule. First, what you have to do, you have to find out the structure, and then you ask certain set of questions, and then you have to step by step find out to which particular point group our in concerned molecule belongs to, right? So that's how we we form the table, a chart which will help us to assign the point group to a molecule very easily. So after we learned about how to form the point groups. So by the way, we also know that these point groups were given certain symbols, and these symbols are known as so-implies notation. And after having gone through this part, we also learned that the presence of certain symmetry elements in a particular molecule will also tell us about certain molecular properties, namely chirality and polarity. So we discussed in quite a bit of detail that how the absence of the SN axis is strictly required in order for a molecule to show chirality or the chiral responses, and those particular point groups which doesn't have any sorts of SN, and when we said this SN, we know that this N can be even this S2. Okay, so any sorts of SN, and at the same time S1 is nothing but the C1. So we learned about the point groups which are intrinsically chiral. For example, like C1, which is always chiral. And we also learned that for point groups which can never be chiral. Okay, so that was one aspect. And also we learned about the how to comment on the polarity of any given particular molecule, because the polarity comes from a particular vectorial quantity called dipole moment. And if there is something like sigma h, okay, or a sigma perpendicular to this dipole moment, or if you have inversion symmetry, then the molecule cannot have a dipole moment, because the effect of this dipole moment in a particular direction will be nullified by these symmetry elements, right? We also learned that how we can find out the effect of applying two or more symmetry operations successively. So how did we do that? We learned two different things which helped us getting the answer of this question, that is, what will happen if I operate two symmetry operations consecutively. So one was group multiplication table, another was stereographic projection. So okay, so here we showed how this enantiomer pair will look like, which are related by mirror image relationship. And this particular molecule was also mentioned earlier, that this molecule belongs to D3 symmetry, which doesn't have any kind of SN. And this mirror image of one particular structure of this molecule, which is like COEN whole 3 type, will have a non-superimposable mirror image, meaning that it will constitute a chiral molecule structure. And so now, we learnt about the group multiplication table, where we saw that all the symmetry operations, because symmetry operations form the point group, right? So for this symmetry point group, the constituting elements are the symmetry operations. Okay, and we learned how to be careful about using the terms symmetry elements and symmetry operation, and where to use what. So on the context of group multiplication table, we learned that we write down the symmetry operations for a particular group in this top as well as on the left side, and then we have the we fill up the rows and columns to get the group multiplication table. Now in an abstract way, we learned how to get the group multiplication table, and we also learned that okay, there are certain numbers of multiplication tables are possible for a particular order of group. Okay, so like for group 3, group 4, group 5, group 6, we learned a certain number of such group multiplication tables are possible. So once we learned this technique, how to form this group multiplication table, then if we encounter with any particular group of having any particular order, then it should have one-to-one correspondence with this particular abstract group, right? So we took an example of this ammonia, which is having an order 6, and that should have one-to-one correspondence between this G6 that was formed in an abstract way. So we showed the similarity, and so in this way, if I know about different G1, G2, G3, G6 and their various possibilities, then one can easily form the group multiplication table for a given molecule. Now this group multiplication table gives me actually the results of operating two symmetry operation one after another, right? So in other way I can say that group multiplication table gives me the products of two symmetry operations. We also learned another technique which was very useful for two reasons. One is, if I know about the point group, then I should be able to tell what are the symmetry operations existing in that particular point group. So symmetry stereographic projection was introduced as a tool for that, and moreover, after learning this stereographic projection, one should be very easily able to find out the result or effect of operating more than one symmetry operation consecutively. So we define what stereographic projection is, and we define how to work on using this particular technique. So we defined the working area, we defined all the particular symbols that are used in these cases, and then we took quite a number of examples. For example, here in this case we showed as a preliminary example taking the point group C2V, and we used any general point and then operated the C2 on that, and then sigma V on that, and then ultimately what we get is a result of the product of these two symmetry operations, right? So using group multiplication table as well as the symmetry projection, stereographic projection, we could find out the result of two symmetry operations operated on any molecule successively. Then we learned about the matrix representation. So after learning all this symmetry and the point group symmetry, using the group theory, we wanted to have even a better mathematical way to have some sort of representation of this these operations, so that we can constitute the representation of the group in a complete mathematical way. So the symmetry operations, either one can draw or one can imagine and get the ultimate result. But in order to be able to use it for practical purpose, one needs to have a mathematical way, and we figured out that matrix is one of the best way to represent these symmetry operations, because this matrix is do the exact same thing as that of the symmetry operations when it is applied on a particular basis functions which is used to form the representation of any given molecule. So in this particular section, what we learned that we have to first find out certain functions and form a set which is known as basis set, and we have to apply each and every symmetry operation on those basis functions. So how did we get those matrix representation? So we first selected certain basis functions forming a basis set, and then based on those basis sets we found the matrices which are which will represent the symmetry operations, such that multiplication of this new matrix with the suppose we have a column vector matrix representing the basis functions, then the product of this new matrix and this matrix containing these basis functions will give me the results that I could easily get using the symmetry operation itself. So in that way, we took a simple example of C2V point group and used a general point having Cartesian coordinates x, y, and z, and thereby we formed the representation for identity C2, sigma b, and sigma b prime, and we got 3 by 3 matrices for each one of them. And once we find out all the matrices for all the symmetry operations, then we put these matrices in place of the symmetry operations, and we call that as a representation of the point group. And we also learned that these matrices are very useful, and even more useful and handy thing is the trace of the matrices. We learned a lot of things about these matrix representations, particularly matrices which belong to a class, that is matrices which are conjugate. So this the trace of the matrix, we call that that is actually called as character of the matrix representation, because these traces bear all the properties of the matrices in a very compact form, and it is very easy to use because we can get the characters even without formation of the matrix. Okay, that we showed in the later part of this course. So we introduced the concept of the presentations which are reducible and which are irreducible. We also learned about how to reduce a representation into the irreducible representations. So we also learnt about the table which is constructed for any given particular point group, and we learned that one particular point group has a table called character table, which contains the exhaustive list of irreducible representation that particular point group can have. And we learnt in detail about the character table. We learnt about each and every region of the character table and what their functions are. We learnt about the properties of this irreducible representation when we learnt about a theory of called the great orthogonality theorem, and we learnt about the consequences of this great orthogonality theorem. We learnt about the properties of each and individual irreducible representation, what is the property of their dimensions, what are the properties of their characters and all. And as one of the consequences, we actually learned how to reduce a representation into the irreducible one. All right, and after learning this great orthogonality theorem, and also learning a little bit about the relation between group theory and quantum mechanics, we started learning about how to construct molecular orbitals by taking linear combinations of this atomic orbitals forming the SALCs, or symmetry adapted linear combinations. So we constructed the symmetry adapted linear combination for quite a few molecules, so that we get the essence of that. So we describe different steps involved in this particular process. So for example, when we took the case of C2H4, we are showing it once again here. So what we did there, we identified the point group first. So, okay, so we started with like finding out the structure using something like VSPR theory or something, and find out the structure, finding the point group, and in the next step we selected a particular set of basis functions. So in this particular case, we selected the 1s orbitals of the hydrogens as the basis functions, and using those basis functions, one has to form the representation. So we did it for each and every molecule that we cared about, and that representation was in the next step reduced to its irreducible representations. And once we figured that irreducible representation, then we formed the projection operators for each and every irreducible representation which is contained within our reducible representation, right? And then we applied these projection operators to find out on this basis functions, to find out what are the ultimate SALCs. So once we found the required SALC, like to start with, we have 4 say atomic orbitals in this particular case of ethylene. So we should get 4 symmetry adapted linear combinations as my molecular orbital, and this SALC, after we formed those, we also verified that okay, they are in accordance with the symmetry properties of the final molecule, right? So in this way we found out all the symmetry adapted linear combinations. So like here, right? After learning about this symmetry adapted linear combination, our aim was to use this SALCs, and we form the molecular orbitals and also assign the energies to them, and later on to find out about the possibilities of electronic or transitions from one molecular orbital to another molecular orbital. So in order to do that, we learned how to set up the secular equation, and in the form of secular determinant, and solve them using certain approximations, okay, which are known as Huckel's approximation, and then we find the energy levels, okay. And also we learned about how to find out orbital coefficients. So we learned about the Huckel's approximation. So though it is approximation, but it is quite good for the purposes that we'd like to serve. So using the Huckel's approximation, we tried to set up the secular equations in form of secular determinants. So what are the steps that we followed here? We first took the atomic orbitals as basis. It's very similar to what we did in case of just formation of SALC. To start with, you form the SALCs, okay, and find out the irreducible components to which they belong to, and then you can you use the projection operator to form this SALCs, and list all these SALCs so that those belonging to a particular representation are together in the list, and after getting the symmetry properties, like to which particular irreducible presentation one SALC belongs to, you club them together. Like for one particular SALC, suppose one particular irreducible presentation, I find 3 SALCs transform as that particular irreducible presentation, then club them together, and then you form the secular determinant, you solve it, apply the Huckel's approximation, and solve for the energies. And once you find the energy, you get the molecular orbitals as a function of energy. So we learned that, and also after getting those molecular orbitals as a function of their energies in the toward the end of the course, when we are dealing with the spectroscopy part, there we learned how to know whether one type of transition from one molecular orbital to another molecular orbital is allowed or disallowed, and we also learned about the intensities that are associated with one of such transitions. And then we learned about the symmetry properties of various types of motions within the molecule. So we talked about translation, rotation, and vibration. So mostly we dealt with the vibrational motion, that is the motion of this internal coordinate where the center of mass remains stationary. We learnt about the degrees of freedom, how to find them out, what are the basis for finding this degrees of freedom out, and we learnt about how to determine the atomic displacements in a given vibrational mode by using theory and Cartesian coordinate, and also how to determine the atomic displacement by for example in like stretching or bending vibration using the internal coordinates. So for example, we took the case of planar N2 F2 molecule, and we systematically figured out what are the normal modes, what are their symmetries, okay, and how the normal modes look like. So how did we do it? We first found out the point group. Okay, we opened the character table of that particular point group, kept it with us because we needed to use it. Okay, very similar to the case of SALCs. And then we figured out that first we took all the Cartesian coordinates on each and every atom as my basis function. So there are 3n number of basis function for any given molecule, and we, for this particular N2F2 molecule, we found a basis set of comprising 12 Cartesian vectors, and we formed the representation, and then in the next step we reduced it. After reducing, we eliminated the contributions coming from translational and rotational motion, and we were left with only those irreducible representations that are related to the genuine vibrational modes. So thereby we figured out that okay, these are the symmetries of the possible normal modes for that particular molecule. So once we have figured that out, then what we did, we used the internal coordinates. So we could select any particular internal coordinates such as the bond distances or the bond angles. So we used for this particular case the NN bond distances and the NNF bond angles to figure out which particular we found out that okay, we have a normal mode which deals with the motion of this NF bond, okay, and they belong to this and this symmetries. So looking at these symmetries, we could easily figure out what will be the nature of each one of these normal modes. Say for example, when we form the representation based on this NF bond distance, we figured out that there are two irreducible presentations according to which this particular NF bond distance they can transform as. So we had at least figured out that there are two normal modes which involves this motion of this NF bonds. Now whichever way that was given by these symmetries like AG or BU symmetries. So knowing the property of this AG and BU, we could very easily tell that okay, one of this motion of NF bond in one normal mode is purely symmetric in nature, so it is symmetric stretching. On the other hand, the other mode is of asymmetric nature, so it was an asymmetric stretching. So in that way we could exactly figure out what are the exact normal modes for this molecule, what are their symmetries, and figure out what in which particular way the atoms in that particular normal mode shows the displacement. Okay, so we learnt about also how to find out the the rules that controls the excitation of different vibrational as well as electronic states. So the main thing here we learned is the application of direct product. So we ultimately have the situation where two states are connected by an operator, which is either a dipole moment operator or its polarizability operator, depending on the case that we are studying. So we constructed a transition moment integral involving this initial and final states, be it vibrational or electronic, and an operator. Okay, so we learned from the relation between group theory and quantum mechanics that each of these wave functions, they form the basis of one of the irreducible representation for that particular molecular point group. So if we know the states, we know the symmetries. So once we know the symmetries, so we can have essentially the direct product between the functions and the operators. If the direct product contain the totally symmetric irreducible representation, then this transition moment integral will survive, otherwise it will vanish. Meaning, if the direct product contain the totally symmetric irreducible representation of the molecular point group, then the transition will be allowed, otherwise the transition will be forbidden. We took certain cases, and in case of molecular electronic transition, what we did is we used the same set of molecular orbitals that was formed by forming the SALCs for naphthalene molecule in one of the classes. We took the same example, so we got a series of molecular orbitals. We took one electron out from one orbital and then put it in the higher energy orbital, and knowing the symmetries of this SALCs, we could find the symmetry of the overall electronic state. So we learned how to find the symmetry of the overall state from the symmetries of the orbitals, and using those states we found out whether one particular transition was allowed or not. So in this way we kind of completed this particular lecture series. So the basic aim of this course was to give you a introduction about the symmetry and group theory, and take you through several relations so that you are able to utilize those techniques to solve certain chemical problems. For example, like finding out whether certain particular orbitals will take part in the molecular orbital formation, whether certain whether we can figure out what is the symmetry of a given normal mode, how will be the normal mode, and also how to find out whether a transition will be allowed or not, how to find out the symmetry of an electronic state, and so on. So using this basic knowledge, one can go to the advanced level where one can actually use it for the problems which are encountered in in one's research life. So for example, someone working in the field of organometallic chemistry, so all the time dealing with metal ligand bonding, so one can actually use the knowledge of this how to form the symmetry adaptive linear combinations, and then how to get the energies of those particular molecular states can be applied on those kind of systems. Okay, someone who is working in the field of say vibrational spectroscopy or Raman spectroscopy, the basic knowledge that we try to get through this course will be extremely valuable when one tries to find out or do some normal mode analysis for a molecule having a larger size, and find out the possibilities of various different type of transition involving the vibrational states within that molecule. So I hope that all of you have enjoyed this course, and I also am extremely hopeful that you learned certain basic stuffs which will be extremely helpful for you in the near future. Thank you for your attention throughout this course, and I wish you all the best. Thank you very much.